Okay, since we had a little bit of data issues, here's exactly what we were doing in the lab. So we were looking at the sum of the forces and velocity in going in circular motion for the rubber stopper. So the mass of the rubber stopper I have on the next page, and at least my radius of curvature. So you guys at least need those two values. And if you remember, we said that the sum of the forces was essentially just equal to the tension force on the rope, since the tension force in the y direction and the force of gravity pretty much equaled out, so your net force was just the tension in the x direction. So this is some sample data. If you look over here, we have velocity and force, and then this is actually what it ended up being graphed. So this was it in just a linear fashion with velocity and some of the forces. If you notice, the r-square value is only 0.91, which isn't really very good. So what I try to do is linearize it because it looks like it's more of a parabolic relationship here, maybe. And when you do that, we get to about a 0.94 r-squared value, which isn't awesome, but it's not awful. So what this ends up getting is if you take the y equals 0.36x minus 0.478, when you sub in your variables, like you're supposed to on your lab report, you get the sum of the forces is equal to 0.0357, and with that, it's 0.0357 newtons per meters squared over seconds squared. And if you remember, a newton is equal to a kilogram per meter second squared. So when you multiply that by seconds squared over meters squared, you are left with kilogram per meter. All right, so there's something in this constant value that has to do with a weight and a distance. Okay, and then because this was a better relationship fit, it's velocity squared. Then if you notice, the y-intercept is 0.478 newtons. Now my maximum forces over here got to about 7.5, and 0.5 is pretty much below 5%, so we can essentially ignore the y-intercept value. So if you look at it on the whole, this is what it ended up looking like. So we have sum of the forces equals to our slope times velocity squared. So this is the mass of the rubber stopper, so you guys can use that for yours. The distance that I had for mine was that, and so you have, when you have a kilogram and a meter, we have both of those. If you divide those, I got about 0.246, somewhat close to 3.57. So this is actually a relationship between the mass of the stopper and the radius of the circle. Okay, so that would mean our forces are equal to our mass divided by our radius times velocity squared. And just for the last part of this, to kind of rearrange it, this is what I want you to write for your general lab equation. Most of the time, you can also represent it. So if you remember, the sum of the forces from Newton's second law is equal to mass times acceleration. So if you divide both sides by mass, you end up getting an acceleration due, this centripetal acceleration, is equal to the velocity squared over the radius of curvature, which just means what your radius is of your circle. Okay, and centripetal acceleration then is the acceleration of an object going around in that circle. Okay, so that's what you need for your lab report. If you need to use my data, you can. If you can kind of use yours and maybe add in a little bit of mine, try and see what you can do. But then that's all you need.